Okay, good morning class. So today we're looking at Euclidean geometry. We're doing the examples on page . We spoke about cyclic quads yesterday and what makes it a cyclic quad and all of those things, not so? So we spoke about the proof of this theorem, not so? We proved this theorem. The link to the proofs will be found in the description box below. Okay, all the Euclidean proofs is in one video from grade 11 and 12. Okay, it's in one video and it will be found, the link will be found in the description box below. Okay, just copy this. Let's go to the next page. So I can delete that one.
Good morning, may I have your attention please?
We spoke about the converse as well. So during our lesson,
please report to Ms. Penter's classroom for your lesson.
During yesterday's lesson we did the examples, but because it was load shedding I didn't have a chance to do the recording there. Okay, so it will benefit you guys by me doing it again. Okay, this is example 1, and example 1 is on page 299. Okay, so I'm just going to go through it. So we are told that in example 1 on page 299, we are told in the accompanying diagram AX and YB are chords that are produced to points D and C respectively, which means to say in that order, such that BC is parallel to AB. So if BC is parallel to AB, what we can conclude that we can use corresponding angles, we can use co-interior angles, and there's no alternate angles that's evident there. So importantly at this point we know that B1 is equal to angle C there. Okay. Then we are told that XY is drawn. You are required to prove that D, C, Y, X is a cyclic quad. Now to prove something is cyclic, we prove one of three cases. What are the three cases? Opposite angles are supplementary. The exterior angle is equal to the interior opposite, and thirdly is the bow tie. The converse of angles in the same segment. So as we can see here, we have an exterior angle. So if we can prove that x1 is equal to c, I've done the job. Not so. Why? Because the exterior angle is equal to the interior opposite. Okay. Now, as I explained yesterday as well, you don't have to introduce the x, but it just makes life so much easier when we're doing proofs of theorems here. Okay, or proving the riders, sorry, not theorems, but the riders. Okay, so we're going to try and prove that angle x1 is equal to angle c. So we start off by either letting x1 be equal to x, or we're going to let angle c equal to x. It doesn't matter. Okay, so we say let, normally one of the two. Okay, let angle x1 equals x. But since there's already an x here, I don't want to confuse you, so I'm going to use a different letter. Let's use, there's a y as well. Let's use A. Okay, let angle x1 be A. So now, if we're wanting to prove that x1 is equal to c, we won't just go straight into it. We have to go to another angle first, the missing link between the two. Okay, so angle x1 is equal to which angle? We said yesterday was be equal to angle B1. Why? So it's angles in the same segment. Are you all okay with that? Alright, so angle B1 is equal to x. So we're saying angle x1 is equal to angle B1, which is equal to A. Why? We see angle in the same segment, and it's coming from arc AY. You don't have to mention the arc. Okay. So angle B1 is also equal to which angle? Angle C. Why? Corresponding angle. So we say angle B1 is equal to angle C, which is equal to A, which is corresponding angles, with DC being parallel to AB. And you see, now we can see that the exterior angle is equal to the interior opposite. Okay, you guys understand? So we state the obvious first. We say since angle x1 is equal to angle C, which is equal to A, therefore we answer the equation. We state the obvious. We answer the equation is then that therefore angle D C YB DCYX is a cyclic chord. Why? Because the exterior angle equals the interior opposite. Okay. In that the reason never mentioned cyclic chord. Okay. Will you guys understand? And yesterday I also indicated that if you didn't want to work with an A way introducing a new variable, then that would have been left out and this here would have been out wherever you see the A. Then you would have just said angle x1 is equal to angle B1, angles in the same segment, angle B1 is equal to angle C, corresponding angles with BC being parallel to AB, and then you can say, then you can conclude, since x1 is equal to angle C, therefore DCYX is a cyclic chord, exterior angle is equal to the interior opposite. As I said, you don't have to bring that A into it. Okay? But you will see me making it a habit of bringing the X and the A and the Y to the party. Okay? It makes things easier. Okay? But if you're that kind of girl who likes life complicated, nah, you can do it with or without. Okay? Well, if you have no problem working with the angles as it is. Alright, people, example 2. And example 2 is on page also 299. Okay. Nope. Okay, here we are told that, let's just pull this down a bit. Here we are told that in the diagram POQ is the diameter. People, if POQ is the diameter, what do we know? R1 and R2 is R2 and R3 is 90 degrees. Why? Angle in semicircle. Chord R is drawn parallel. So R is drawn parallel to PQ. What do we know then? We can use alternate angles. So P1 is 24 degrees, as you can see. Can you see that? Alright. And you can use co-interior if needed. There is no corresponding angles, that's everybody. Then we are told that those lines are drawn. First question is calculate O1. But we know that O1, angle at center, is twice angle at circumference. So I need to know what P1 is. Not so. But we already spoke about P1. P1 is going to be 24. So we got A. So we say firstly that angle P1 is equal to 24 degrees. Why? It's alternate angles with SR being parallel to PQ. There's 24 degrees. Okay. Then we said O1 is double that. So O1 is 2 times 24, which is 48 degrees. Why? Angle at center is equal to 2 times angle at circumference. Okay. Here's 48 degrees. Okay. Let's look at B. Question B, they want to know the size of angle Q. Okay, now there's two ways for doing angle Q. Firstly, we can say that is radii. So angle Q is equal to angle R3, angles opposite equal sides, and then say angle Q plus R3, which is also Q, They must equal now. Plus 48 equal to 180, sum of triangles. And then you work out angle Q there. Or we can work with that triangle here. Okay, because the angles in the triangle adds up to 180. We know that that angle is 90 degrees. Why is that angle 90? Because angle in semicircle. Okay, so we need to first say that that is 90. So we say that P or Q is equal to 90 degrees. Why? Angle in semicircle. Now we can say that angle Q is equal to 180 minus 90 minus 24 degrees. Why? Sum of triangles, and it's triangle Q or P. Again, you don't have to name the triangle in. So angle Q works out to be what? 66 degrees. Okay. You all okay with that? What I'm going to do is I'm going to take this off here, as I need to keep the diagram in focus. And also, as you can see, you guys must do the same. You fill in on the diagram. You start populating your answers on the diagram. Okay? People can see, they ask you to calculate angle S. Angle S, which is this angle here. So what do we notice about P, Q, R, S? The four corners, the four vertices, are touching the circumference of a circle, which makes this what? Cyclic quad. So opposite angles in the cyclic quad is supplementary. Not so? So angle S plus 66 degrees equals 180. Opposite angles of cyclic quad. Angle S works out to be 100. Okay, and with that you were able to do exercise 9.5 on page 3. Alright? I'll stop this video and I will explain now the next example. Okay. Tangents.